Let us start the last or almost last but one chapter in this series of lectures on thermodynamics of electrochemical cells, lecture 12. It is a potentiometric titration. Before going to this potentiometric titration, I like to explain what is meant by titration. Titration is a process of chemical analysis in which one constituent in a sample is determined by means of a titrant which is taken in a bullet. And this equivalent, whenever one component or the constituent of this titer, and this is the titer. I can give a sketch. This is a beaker. Here is it is called titer. Titer. It contains the sample solution. Sample solution which contains the constituent whose concentration or mass or amount is to be determined. Known amount of these sample solutions is taken by means of a burette, by means of a pipette, and let it be V1 cc of strength S1. This is the volume and S1 is the strength of this constituent whose value is not known to us. And here one burette called titrant. Here the titrant is taken in a burette of a known concentration. This is the arrangement of these titrations. And whenever one equivalent of this constituent reacts with this one equivalent of this titrant, we get this equivalence point. And experimentally this equivalence point is determined by means of a signal to mark the end point of this titration. And this equivalence point and end point, the difference between the two is the titration error. We always want this titration error to be minimized by suitable choice of this endpoint signal and the method of detecting this signal. In some cases, suppose one indicator, if we add some indicator from this outside to this titer, then this indicator will change its color just when this constituent substance in this titer is totally reacted with this titrant, and this in this case the signal is the visual color change. And in some cases, not only that, in some but we have to choose a suitable indicator so that the signal becomes just near the equivalence point of this reaction. Or in some other cases, the electrical properties are also utilized to determine this end point of these titrations. Suppose the potential of an electrode dipped into this titer, and the potential of this electrode, which is called the indicator electrode, will change with the concentrations of this constituent component in this sample solution. Or in some cases, the conductance of this titer solutions is being measured time to time with this gradual additions of this titrant from this burette. And in other cases, the electrical current is passing through these solutions, and this is utilized to determine this end point of this titration. In all the cases, at this end point, there is a sharp change or the abrupt change of this electrode potential or the conductance or the current passing through these solutions. Today, I shall discuss only the potentiometric titrations, where the potential of an electrode is used to determine the end point of this titration. And in this case, suppose one suitable electrode, which is called the indicator electrode, whose potential depends on the concentration of the constituent in this sample solution depends. So this choice of this indicator electrode is a very vital one. Since this electrode of this potential of this single electrode is not determined, so we have to couple this indicator electrode with a standard secondary electrode whose potential will not change with the course of this titrations. Then we are getting a cell, and cell potential is determined by means of potentiometer, or in some cases electrometer or the vacuum potentiometer. So this first one, this potentiometric titration, becomes of various types depending on these reactions, and say acid base, one potentiometric titration depending on this acid base reactions, another is precipitation reactions, and the redox reactions, and the complex reactions, and so on. Let us first discuss the potentiometric titrations by the use of on the basis of the acid base reaction. In this case, this acid is generally taken in a titer, and this HA reacts with this base BOH. Base is taken in this burette and giving this salt BA, and these are all in solutions, aqueous, and this is also aqueous, and giving this BA aqueous plus water liquid. So naturally it is seen that the hydrogen ion in this titer is getting decreased by the additions of this alkali from this burette. So naturally we shall have to choose an indicator electrode whose potential depends on the concentration of this hydrogen ions. The queen hydron electrode is the best one to set up in this laboratory, or a more accurate glass electrode may be used, but in case of glass electrode, ordinary potentiometer will not be used. and hydrogen electrode is generally avoided due to its complication to set up in this laboratory. So to here, if we use this queen hydrogen electrode to determine this queen hydrogen electrode as this indicator electrode, then we can set up a cell here, this saturated calomel electrode and this salt bridge and the acid solution. Acid solution, say it is the titer. It is the titer saturated with queen hydrogen. Queen hydrogen QH and here the platinum is the connecting metal, and this one is the positive electrode and this one is the negative electrode, and this is the shell. And the E shell EMF of this cell is determined by, in this case, by means of potentiometer, and this is E, and this queen hydrogen electrode potential minus E, and this saturated calomel electrode. And this one we already know 0.699 is the standard potential of this queen hydrogen electrode, minus 0.059 pH at 25 degrees centigrade, and minus this saturated calomel electrode is 0.2415 volt. So actually this E cell depends on this pH of this acid solution, which is taken in this titer. So differentiating this one 0.4575 minus 0.059 and pH. This is E cell potential is determined time to time with the gradual addition of this sodium hydroxide or any alkali from this burette. And whenever this alkali is being added, pH is increased and E cell is decreased. But at this equivalence point, there will be a sharp increase of this pH, as we have already know. This here it is a pH of this solutions, and here the volume of this alkali, or the titrate, volume of this alkali or titrate. And this curve will be like this, and this is the end point. And if we plot this E cell, here E cell and volume of this is alkali, and then it becomes like that, and this one is the equivalence point. This can be taken as this P2. P2 is the volume of this alkali required to complete reactions with this acid taken in a titer. And we know generally this V1S1 equal to V2S2. This is the formula. V1 is the volume of this titer taken by means of a pipette. S1 is the strength of this acid, and V2 is the volume of this titrant or the alkali taken in a burette. This is V2, and S2 is the strength of this alkali, which is known to us. So S from this, if we know this S2, then S1 will be determinant which will give the concentrations of this acid solutions taken in this titer. And this graph and the symmetry of this graph depends on the strength of this acid and alkali taken. If these two are the strong, acid and alkali, if both are strong, suppose this is HCl and this is sodium hydroxide, in this case this card is very beautiful, and it is totally this change is also very sharp, and end point could easily be determined. If we use the weak acid in this titer, and it is the strong alkali, then actually this curve will be little bit the curve will give you the such nature that the end point of this titrations is very difficult to determine. Suppose whenever this weak acid is taken, it is the volume of this alkali, and this is the E cell, and in this case this curve will be like this. More the weak of this acid, this curve is more inclined and difficult to determine this end point of this titration. In this case, the differential curve del E by del V means it is the slope of this curve, and here it is the V the volume of this alkali. In this case, this will be and this one is the V2 differential form, and this differential form of this curve will give very easy to determine the end point of this titrations, and then we can use this equation. Not only that, one very important factor is that the approximately the dissociation constant of this weak acid could be evaluated from this potentiometric titrations. As for example, say suppose this is the equivalence point of V2, and then suppose this one is V2. Then this is the V2 by 2. V2 by 2 means in this case the acid is half neutralized, and E1 may be taken as the potential of this cell when this weak acid is half neutralized, and from this E1 then we can put here this E1 equal to 0.4575 minus 0.059 and pH, and this is the pH of this weak acid at which the weak acid is half neutralized. And according to the Henderson equations, we should know this pH equal to pKa plus log salt by acid. Salt of this weak acid, and this is weak acid. So whenever the weak acid is half neutralized, this ratio becomes 1 and log 1 equal to 0, and this will give you this pKa, and this pKa then equal pKa of this weak acid is then equal to 0 point from this equation 0.4575 minus E1 and divided by 0.059. This one is the pK of this weak acid, and the approximate value of this pK could be determined as the site utility of this potentiometric titrations. Here this pH here. And not only that, we can determine the we can titrate the diabasic acid like oxalic acid, where the first dissociation constant is greater than equal to 100 K2. In this case, 2 inflections we can get it. And if we take this oxalic acid in this titer, then this curve will be, this is E cell and this is B, volume of this alkali, and this one will give like this 2 inflections, and it is the first inflection, so this is the second inflections, and these 2 inflections will indicate, and here V2 is the volume of this alkali required to complete neutralize this oxalic acid. And from this curve, like the before, we can also determine this K1 and PK1 and PK2 of this oxalic acid. And you know this not only that, if you taking instead of oxalic acid a mixture of 2 acids, one is strong acid and other is weak acid, suppose hydrochloric acid and acetic acid, then this type of curve we can also obtain, and the first inflections will give here this curve will be like this, and this one E del E by del V in this y-axis, and here it is V, and here V1 and here V2 and here V2 dash. In this case, whenever we are taking this hydrochloric acid and acetic acid in this titer, then V2 dash will give you the volume of this alkali required to neutralize this hydrochloric acid, and V2 minus V2 dash will give this value for this acetic acid. This is the all about potentiometric titrations depending on this acid base reactions. Now we shall discuss the second type. Now I shall discuss the second type of potentiometric titrations depending on a precipitation reactions. Here the ion or the constituent ion whose value is to be determined is being removed by precipitation with this reagent taken in a burette. One very important example is that the silver nitrate solution could be titrated with sodium chloride solutions. And these reactions all known. This silver nitrate is taken in this titer, and by means of measure amount of V1 cc by means of a pipette, and this sodium chloride solution is added from this burette and gives this silver chloride solid and plus sodium nitrate aqueous. So in this case, the silver ion is being removed from this titer by as a precipitate with the silver as silver chloride. And this is so we must have to choose an indicator electrode whose potential depends on the concentration of this silver ion in this titer. And in this case, the silver ion silver. In this case, silver ion silver is the best indicator electrode to determine these titrations. And actually, if we like to make a complete cell, then here the saturated calomel electrode and this salt bridge and here the silver nitrate solution taken in this titer, and here the silver metal solid is dipped into the solutions, and this one is the cathode and this one is the anode. It is to be remembered that in this case potassium chloride could not be used in this salt bridge. If we use this potassium chloride, then this chloride reacts with this chloride ion of this potassium chloride in the salt bridge, reacts with this silver ion and forming the precipitate and block the mouth of this or the two ends of this salt bridge. We can use this ammonium nitrate. We can use this ammonium nitrate in this salt bridge to avoid such type of complications. And this E shell, in this case, E cell will be equal to E of this silver ion oblique silver minus E of this saturated calomel electrode. And this value actually it is E naught, this E naught value and E naught value is 0.6999 plus 0.059 and log activity of this silver ion and this saturated calomel electrode potential is 0.2415 and its value remains fixed during the course of titrations. So if we do these calculations, then 5 and 5 and then 7 and then 5 and 0.5 plus 0.059 log activity of this silver ion in this titer. As the titration is going on, as the titration proceeds, the silver ion is removed from this titer solutions, and the cell potential is also decreasing, and we get this similar plot E here, and the volume of this silver chloride, volume of this sodium chloride, sodium chloride is taken as this titrate, and this curve will be like this. If we draw the differential plot, then del E by del V differential plot, and this is the slope of this curve here V, and this curve will be like this, and this is the end point of this titration. So similarly, we can also take this sodium chloride in this title and silver nitrate in this titrant. And in this case, the chloride ion in the sodium chloride is being removed by reactions with the silver nitrate from this burette, and the indicator electrode will be in this case this chloride ion and silver chloride solid and silver. This may be taken as this indicator electrode to titrate the sodium chloride solutions by silver nitrate solutions. One additional quality or additional term or the constant we can also get here, and this is V2. And suppose this is V2, and at this V2 we know this. Suppose this is E1. E1 is the potential. Whenever E1 is the potential of this cell at this equivalence point. So putting E1 here, E1 equal to 0.5575 minus 0 plus 0.059 and log activity of this silver ion. So putting E1, we can get this activity of silver ion at this equivalence point. And we know just at this equivalence point, the activity of this silver ion becomes equal to the activity of this chloride ion. Then the solubility product of this silver chloride will be equal to activity of the silver ion into activity of this chloride ion, and this one will be activity of a silver ion squared. So from this activity of silver ion could be obtained, and here it will be squared up and gives this solubility product of this silver chloride in addition to this titrations value. In this case, the third type of reactions, oxidation-reduction reactions, and potentiometrically this type of reactions could also be titrated. As for example, say the titer. In the case of a titer which contains some reducing agent and the titrant oxidizing agent, and this is simply a platinum wire is dipped into the solutions of this titer, which acts as the indicator electrode. And the example, say the ferrous sulfate ion can be titrated with ferric ion. That means ferrous sulfate I can take in this titer solutions, and this ferric sulfate in this burette. And this reaction is, if ionic reactions, I can write this ferrous ion. This is in titer, and plus ferric ion, and this is in the titrant, and gives this ferric ion plus the ferrous ion. That means this ferrous ion is oxidized to ferric ion, and by the additions of this ferric ion. And in this case, this ferrous sulfate have been taken in this titer. The potential of this electrode will change with this depletions of this with the oxidations of this ferrous ion to ferric ion, and the cell, one cell set up, and cell is to be set up to combine with another saturated calomel electrode, and this is the salt bridge, and this one is the negative electrode, means anode, and here this ferric ion and ferrous ion, and these solutions are taken, and here this platinum electrode connecting, and this one is the cathode. This is the simplest cell, and the potential of the cell is determined by means of potentiometer, and this E cell is equal to E of this ferric ion and ferrous ion in solutions, and this platinum, and minus E of this standard calomel electrode. And then this one actually 0.771, it is the standard electrode potential of this ferric ferrous system, reduction potentials, and plus 0.059 and log, and instead of activity we can write this concentration of the oxidized species and reduced state of this reduced state of this species, and this one, and minus 0.2415 volt, which is the potential of this standard calomel electrode. If we do this, then E cell equal to, this one will be subtracted here, then 5, and then 5, and then 9, and then it is 3 and 4. It is 4. And this subtraction actually 2, 9, 10, 11, 11, and then 7, 5, and this one 2, 9, 9, and 5, yeah, 2, and then it is 5, and plus 0.059 and log this ferric state concentration and this ferrous state concentration. And as this ferric ion is added to from this burette, this ferrous ion is converted into ferric ion, and this one is decreased, this one is increased, ratio is also increased, and so E cell will also be increased accordingly. At this equivalence point, the E cell will change very high dramatically, and this could be shown as like this. Here E cell in this y-axis, and volume of this ferric sulfate in this x-axis, and this curve will be like this. And whenever if we plot del E by del V, plot in these directions, then it will be, and this is the end point V2. So so this curve as this slope is increasing, and so as this E is increasing with this V and slope is positive, and this curve it will be like this, unlike the other curve so which I have shown earlier. And at this potential of this indicator electrode here, potential of this indicator electrode at the start is undefined, as this there might be a trace of ferric ion, but its concentration is not known, and so this one is undefined, and so E cell starting point is undefined. And at the after the start of this reaction, the potential of this indicator electrode is controlled by ferric ferrous system, and this E of this I indicator of this potential of this indicator electrode will be controlled by this ferric ferrous system. Means this E naught and ferric and ferrous and platinum and plus 0.059 and log here ferric on, and here is the ferrous on. That means this value is 0.771 and this value is plus 0.059, and we can also write as F divided by 1 minus F, where F is the fraction of the ferrous ion is titrated or extent of titrations. And this equivalence point, when this extent of reaction will be 50%, then F will be 0.5 and this indicator electrode will show. And at this equivalence point, this indicator, the indicator potential will be this N1 and E1 naught plus N2 and E2 naught divided by N1 plus N2. N1 and N2, these are the number of electrons changing in these two systems. This is for this titer and this is for the titan. In this case, in our case, N1 and N2 equal to 1. So 1 into E naught and this ferrous ion plus 1 into E naught and ferric and serous ion and divided by 2. That means here it is 0.771, and for this value it is 1.44 and divided by 2. This volt. After this end point, after this equivalence point, actually this potential of this indicator electrode is controlled by ferric ferrous systems. So in this case, this END after this equivalence point will be E naught and C4 plus Ce3 plus, and here platinum and plus 0.059 by 1 into log concentration of ferric ion and divided by concentration of ferrous ion. And it's writing in terms of this fraction. This is 1.44 at 25 degrees centigrade plus 0.059 and log. This is equal to F divided by 1 minus this is equal to F minus 1. So this is all about these oxidation reduction reactions, and I can also set one example, one problem which has been set in IIT exam 2007, and the next one, this 4. The last one, I can also illustrate this potentiometric titrations on the basis of this complex reaction. So suppose we like to estimate the zinc ion in a sample solutions. Then I shall have to take up this one indicator electrode, means Zn2 plus oblique Zn. This can act as the indicator electrode, and this titrate in the burette I shall use this disodium salt of EDTA, and whenever this EDTA have been added to this zinc ion solutions, zinc will combine and becomes complex and removed from this titrate. So the potential of this one, the potential of this electrode will also change accordingly as the zinc ion is being removed. After the end point, this value will take a long jump, and this again this electrode, the potential of a single electrode could not be determined, so it could be combined with a secondary standard electrode. Now I shall give you one problem. It is to be remembered that while we are drawing this curve for this potentiometric titrations, the data points at this end point or the equivalence point is very important to draw a very accurate, to get this very accurate end point of this titrations. Unlike in this conductometric titrations, data point away from this end point is important, and this is the another thing to be noted up. And in case of redox reactions, and I can set one example here. So one thing is very common, this titer should be at least 10 to 100 times greater than the concentrations of the titrate. Concentration of the titrate must be greater than 10 or 10 to 100 times greater than the concentrations of this titer to avoid the dilution effect. These are all things already I have discussed, and in case of other chapters like conductance chapters. And the solution, the problem is IIT Jam 2007, a 50 ml 0.05 molar solutions of ferrous ion is titrated with the 0.05 molar solutions of this steric ion in the presence of this dilute sulfuric acid at 25 degrees centigrade. Calculate the equivalence point potential and the equivalent constant in terms of log K. Given this standard values of these two systems are given here. So equivalence, the potential at this equivalence point will be this one by 2 equal to 1.1 volt, and the reaction is ferrous converted into ferric. Ferrous is oxidized, ferric is reduced. So the cell setup is at this anode there will be ferrous system, and this cathode ferric systems, and the E cell naught equal to right minus E naught, right hand side electrode minus E naught left hand side electrode, and these values are given here, and it is found to be 0.60 volt. So E cell naught, we have the standard formula, E cell naught divided by N, and N equal to 1 here. So log K equal to log K equal to E cell naught equal to 0.60 into 1 divided by 0.05 and almost equal to 10. So this is all about this potentiometric titrations. I have discussed in details. Maybe some part of this portion may be left out unknowingly, and these are the potentiometric titrations. So we give the very accurate value of this end point of this titrations, and the titration error is very much minimum. And next class in this thermodynamic of electrochemical cells will be the commercial cells, and that will be the last one in this chapter. Then after I shall discuss I shall start another chapter, thermodynamics, which is very important for IIT JEE students also, IIT JEE, NEET and the state JEE, and in all the cases. So that chapter, thermodynamics, is the basic chapter in chemistry. So thanks to you all who are watching this video. You subscribe if you like this video.